pro studenty, kterým nevadí sedět na zemi, si sednou se úplně do první řady před všechny lavice na zem. Tak a teď naopak pro lidi, kteří by opravdu potřebovali sedět, tak tamhle si ještě asi volných 5 míst. Jo, těhotní, důchodci, těhotní důchodci.
Good evening, ladies and gentlemen. Dobrý večer, dámy a pánové. And welcome to today's public lecture. Vítám vás na dnešní veřejné přednášce. As you may know, this event is actually part of a conference which is organized in honor of Professor Jiří Bičák, who is a gravitational physicist in Prague, who unfortunately passed away about a year ago. So let me tell you a little bit about Jiří. So Professor Jiří Bičák was the father of Prague's general relativity group. So basically everybody who's doing general relativity in Czech Republic or beyond is his student or student of his student, and so on. So Jiří was a truly Renaissance person. So he's a very charismatic person, very social person. If you met him once in your life, you would remember him for the rest of your life. He was always at the center of everything that happened. So imagine a very calm evening, nothing is happening. Jiří comes in and things start happening. Jiří used to play guitar, and so he would sing rock and rolls, he would sing spirituals. He would also play violin and sing Christmas carols. He would force us to sing one particular Christmas carol every Christmas party. And we would have to stand, and he would play the violin, and he would sing, and everybody would have to just listen and do what he wants. He was an amazing lecturer. He would enrich his lectures with history and art explorations. He would enrich his lectures with very interesting stories. Sometimes the story started, and it was like with Schweik. The story continued to another story, and you would never return back to the lecture or the original idea, but it was very, very entertaining and very, very amazing. And as I said, he was a Renaissance person. He had very broad interests, which ranged from physics, chemistry, religion, art, and so many things. And he had very deep insights into all these subjects. Jiří was also a very international figure. So he would go every summer to the University of Cambridge, where he would spend 3 months working with the most esteemed colleagues in the field. He would go to Max Planck Institute every winter. So he would basically never be in Prague. So this picture is actually taken from his visit at the Perimeter Institute in Canada. This is in front of the Niagara Falls. You probably recognize that. So basically he was known all around the world. So now to the lecture. So let me first tell you about the event. So the event is actually organized, as I said, as a part of this conference. And the conference is organized by the Institute of Theoretical Physics at the Charles University, and also by the Astronomical Institute of the Czech Academy of Sciences. So in particular, this event is sponsored by this space for the humankind, Vesmír pro lidstvo, which is like an initiative of the Czech Academy of Sciences to actually connect to people and to do some outreach of what Czech Academy of Sciences is doing. And so, without further ado, let me now introduce to you Kip Thorne.
It's great pleasure and honor to have here one of the gurus of our branch of physics, of theoretical physics as such, and mainly of gravitational physics, Nobel Prize winner, Professor Kip Thorne. In order to persuade you that we need such gurus, so I will make experiment. We all here probably are theorists, but I will perform an experiment. Jiří Bičák, sorry. Jiří Bičák was telling us that this is quite important experiment to persuade you that one needs better theory than Newtonian for gravity. Because you saw how this book is falling through light rays whose propagation is described by Maxwell theory. Whereas if you use Newton's theory for the fall of the book, so these two theories are incompatible. So we need something better. And so now I will tell you something about Kip. Kip Thorne started Professor Thorne obtained his bachelor degree in physics from the California Institute of Technology, and then he continued for master and PhD in physics at Princeton University, where his supervisor was John Archibald Wheeler. And already in 1970, at his age of 30, he became professor of theoretical physics at Caltech. Later, also at Caltech, he became the William Cannon Professor. It was in 1981, and then finally, very prestigious position of the Feynman Professor of Theoretical Physics. It was in 1991. And in Wikipedia, you can find that he himself cultivated about 50 physicists who received PhDs under his supervision. He was, of course, also scientific advisor for Interstellar movie, and he also appeared in the Big Bang Theory. And as you probably know, his own research mainly concerns black holes, relativistic stars, and gravitational waves. Kip Thorne was one of the leaders of the whole collaboration of LIGO-Virgo group who successfully measured gravitational waves finally, and this was probably the main reason for the Nobel Prize. But for us, he was guru for all his life almost. So anyway, this Nobel Prize is for, I would say, a lifelong achievement. He is also expert in more adventurous beasts, adventurous beasts than black holes and relativistic stars, also in time machines and wormholes and objects which are close to them. I remember that as students, because Jiří was very often referring to Kip, so we very much admired him, but I must say that we also envied him, because Jiří told us that you make your calculations usually in a bar where there was quite a liberal entertainment going on the stage. So imagine that it was in communist times when we were students, so we were really nervous about that. Finally, I wanted to, on this lighter note, I wanted to tell you one joke, which is not a joke, which is a real story. When Professor Thorne was here in 2019, it was, And we went for a dinner together with our dean and of course with Jiří and also with Pavel and David Vokrohlický and with our wives. So at that time, my wife Zuzana was booked to a hairdresser's. And she was booked for Thursday, but the dinner was on Wednesday. And so Zuzana on Monday went there and told the hairdressers, well, sorry, I must come on Wednesday, at most on Wednesday. And he was saying, well, why you need it? Well, there will be important dinner, and so I must go there. And he asked, and with him. And she said, well, with Kip. And he immediately reacted, oh, Thorne! So this is to show you that you are really popular here. So last but not least, on Sunday, Kip will be 85. So let us... So congratulations and welcome again in Prague.
Yes.
It is very appropriate that Jitka, daughter of Professor Bičák, is giving this flower to Kip. So,
and she told me it is from her father. Let me give it to my wife. Now, I'll begin the way Stephen Hawking always began his lectures. Can you hear me? Okay, good. So it's a great pleasure and honor to be here at this conference in memory of Jiří Bičák, and I'll talk about Jiří in a few minutes. Let me just say that my lecture, this is going to be different from any lecture I've given before. The early part is going to be quite personal, and a lot of it will be by my connections to Prague physics and to Jiří, to Karel Kuchař, who was one of the mentors of Jiří, and a dear friend of mine as well. And in the context, that's in the context of the very early period of research on what I like to call the warp side of our universe. And after going through some introductory things about that period, which was a very exciting period for Jiří and for me, I'm going to move into an aspect of the warp side of our universe that I have rarely lectured about and only started lecturing about very recently, which is a strange sounding topic, but it is a topic that I think is really quite exciting and has great import for the future as well as the past. It's called vacuum fluctuations in cosmology, in astrophysics, in high technology. So that's where I'm going. But I began in 1962 when I went to Princeton University expressly to study with John Archibald Wheeler. John Wheeler was the great guru of relativity in that era. Now, 1962 was a period when we had almost no observational evidence about a relevance of general relativity to our universe. But John Wheeler and others, a handful of theoretical physicists, were beginning to talk about this in very exciting terms. And it was from John that I learned that there might be what today I call, though he didn't use this precise phrase, a warped side to our universe. And by this I mean objects and phenomena that are not made from matter like you and I, but rather they're made from warped space and time. And examples that I will talk about are black holes, wormholes, the Big Bang singularity in which our universe, we believe, was born, gravitational waves. There at that time was no observational evidence for any of these except the Big Bang. We did have observational evidence that the universe was expanding out of something which had been given the name Big Bang. However, over the next decade, this would change hugely, and I'm going to talk about that next decade in this introductory part of this lecture. I like to call it the golden age of warp side research, the golden age of research on the warp side of our universe. It's what got us started as physicists and astronomers in exploring the possibility of this warp side of our universe. The very first evidence that there really was a warp side of our universe above and beyond the Big Bang in which the universe was born came on February 1963 when Martin Schmidt, back at Caltech, I was now at Princeton, I had been at Caltech as an undergraduate, when Martin Schmidt discovered quasars. And what he observed was this. He saw a very, very bright object in this image. It looks extremely bright, but that's because the image is overexposed in order that you be able to see this jet that's sticking out of it, this flying out from that source of radiation. In reality, that source of radiation is very, very tiny. It's just overexposed in this picture. And then there's this jet coming out of it. And he took spectra from which he could infer how fast this object was moving away from the Earth. And he discovered this object was moving away from the Earth at 16% of the speed of light. And that was just phenomenal at that time, that there would be an object that was actually very bright as astronomical objects go, receding at 16% of the speed of light. And he could also infer how far away it was, that it is 2 billion light years from Earth. That's a heck of a long ways from Earth. The size of our observable universe is only about 10 times that, a little less than 10 times that. And he inferred that the luminosity of this was the same as 2 trillion suns, 2,000 billion suns, 2 million suns. Unbelievable luminosity. And from this he inferred that he didn't infer very gradually over a period of about 10 years thereafter, more and more observations of this and other quasars and theoretical work related to them made it clear that this object is powered by a huge black hole, and that what you're seeing is emission from hot gas orbiting around the black hole and a jet that has been ejected by the black hole from its vicinity. Quite phenomenal. Summer 1963, this is just a few months later, and everybody's very excited about these quasars, trying to understand what they were. We only really understood they were black holes, as I say, a few years later. I went to a summer school on theoretical physics in the French Alps, the École d'été de physique théorique. And this was in Les Ouches, France. And so this is a photograph that I think I took, looking down from the school, and you see up here, Mont Blanc is up above there, and you're looking over here at the, I think, a Guy de Midi. And this is the Chamonix Valley down below, just an idyllic place where I learned relativity in depth for the first time at this summer school. And here is the lecture hall is back inside here, as well as a library. This school was founded by Cecile DeWitt, who had been a postdoc of Einstein's, and who at the end of World War II, who had been a teenager in World War II. And after the war, and after she got her PhD, she built this school in order to recreate physics, rebuild physics in Europe through bringing in lecturers from around the world, having half European students and half students from outside Europe there. And it was a marvelous place for me to learn relativity. I learned about black holes, neutron stars, stars that are so dense that they're made of pure nuclear matter, hypothetical stars. There's no evidence for black holes. There's no evidence for neutron stars, observational yet. Geometrodynamics, the dynamical oscillations of warp space-time, no evidence at all for that, but John Wheeler lectured about that. Ray Sachs lectured about the theory of gravitational waves, and Joseph Weber lectured about gravitational wave experiment. He was in the process of building his first gravitational wave detectors to try to search for gravitational waves. It was a really exciting period, but again, we didn't have any observational data on anything related to this except the quasars. This is a photograph, again, of the school. This is a path going down the school to the cafeteria down here, and from the school up on the right. And at this school, I met Karol Kukosz. And Karol was a wonderful human being. He was kind, he was gentle, he was brilliant. He was a mathematical physicist. I'm not a mathematical physicist. He had an ability to work with the mathematics of general relativity that was far, far beyond anything I could ever even aspire to have. And we became very, very close friends. And it was perhaps, it was certainly one of the very nicest parts of being there at this summer school. And in terms of personal relationships, it was the most important personal relationship I developed at that school. 1964, the following year, cosmic microwave radiation was discovered by Arno Penzias and Bob Wilson using this great big dish. It was a radio dish that was built in order to get signals from satellites. This was a very, very early period of satellites orbiting around the Earth. And they had excess noise in this antenna. I was back at Princeton. Bob Dickey, a professor at Princeton, was beginning to build an instrument to search for microwaves from the Big Bang, which he was almost sure were there. And when he heard they had excess noise in their antenna, he said to himself, they have probably seen the radiation that I'm out to search for. And so he went up and talked to them, he and Jim Peebles, his young associate. And sure enough, that's what they had, and he explained to them, and they got the Nobel Prize, and Bob Dickey didn't, but they certainly earned it. This great discovery, fantastic discovery, hot microwaves left over from the Big Bang. So now we had two pieces of observational data about the aspects or an era of the universe in which general relativity was very important, when the universe was just a few hundred thousand years old, when this radiation was released from the hot gas and able to propagate, and an ability to explore then those very early epochs of the universe. 1 year later, I was lecturing at a summer school in Verona, Italy, and afterwards, my wife and I, Linda and I, went to visit Karol Kukosz in Prague. And it was just wonderful seeing Prague, the city that had not been damaged very much at all in World War II. Prague very quickly became my favorite city in Europe, and always has been ever since then. We visited with Karol and his wife Vladina and their daughter Kamala, and we just had a wonderful time here for about a week, staying with them in their apartment. 2 years later, in 1967, there was an International Astronomical Union meeting in Prague, and I'm almost sure that some of the bigger sessions were held in this lecture hall, though it has been refurbished a little bit since that time. So I came, and my wife Linda came with me. Again, we stayed with Karol and Vladina, and I went to the sessions of the International Astronomical Union, and there I met Jiří Bičák, Karel introduced me to Jiří. Jiří was a student that Karel was mentoring. And I was just so impressed with Jiří. Again, like Karel, superb mathematical abilities and depth of understanding of physics, a superb spirit, a gentleness about him. And I just remember thinking, my gosh, these Prague physicists, they're so different than physicists elsewhere in the world. But I also met for the first time Jakub Borisovich Zeldovich. Zeldovich had been with Andrei Sakharov. He was one of the creators of the Russian hydrogen bomb. And John Archibald Wheeler, whom was my mentor, was one of the creators of the American hydrogen bomb. And after that period of working on thermonuclear weapons in the 1950s, Zeldovich and Wheeler left their weapons work and both moved into astrophysics. And they became friends and colleagues, and I became a mentee of both of them. That is, I was mentored really by Zeldovich just about as much as I was by John Wheeler through a number of subsequent visits to Moscow. But Igor Novikov, who was a postdoc with, what I would call a postdoc with Zeldovich at the time, he got his PhD several years earlier. He and Zeldovich at this IAU meeting, I am almost sure in this room, they described how to search for black holes. A wonderful way to search for black holes. They said, if you have a star and a black hole that are orbiting around each other, so here's the star, the black hole is over there, it's very, very small compared to the star, but it will weigh roughly the same thing as a star, or maybe even more. They orbit around each other. And if there's a wind off the star, much of the wind will be grabbed gravitationally by the black hole and sucked in. And as it goes in, there will be shock waves around the black hole, and you will get X-rays coming off from those shock waves that form around the black hole. Or this infalling gas may even form a disk of hot gas around it, an accretion disk, again emitting X-rays. So they said, look for a black hole, which you can't see any light or radio waves, any electromagnetic waves coming from it, and a star. So the star is orbiting around something dark and heavy, and the dark, heavy object is emitting X-rays. And so that was their challenge to the observational astronomers, X-rays coming off. Remember that, because we're not there with observational data yet, but that was a key prediction. 1967, Jocelyn Bell at Mullard Radio Astronomy Observatory, using instruments that had been designed and built by her PhD advisor, Tony Hewish, she discovered pulsars, objects from which very regularly pulsed emission of radio waves were coming, boop, 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 just like that. One every second, for example, or every few seconds, or even a fraction of a second. And at first, they facetiously called this little green man LGM, and they were LGM1, LGM2, LGM3. That was facetious. But it was very hard to understand how something could have such regular pulsing. But they were soon shown to be spinning neutron stars. So you have a neutron star here, and it's spinning around a vertical axis, and it has a magnetic field where you see those magnetic field lines shown here in blue. And through effects of what's called magnetohydrodynamics, jets are shooting out from the neutron star. And this jet then is also emitting radio waves coming off from electrons spiraling in the magnetic field that are accelerated near this neutron star. That's what was figured out is going on. And as the neutron star spun around its axis, every time the radio beam swung past Earth, you saw a beep. And that was really quite startling. But neutron stars had been predicted way back in the 1930s. Originally, by Walter Baade and Fritz Zwicky. And there had been a lot of theoretical work done on neutron stars, particularly by John Wheeler and his students. And so this was actually the confirmation now of the existence of these stars, and a challenge then to build a detailed theory of these stars, of their structure, and of how they produce this kind of emission. Again, general relativity is much involved because gravity around the neutron star was extremely strong, so strong that space and time are highly warped near this star. 1968, January 11th, John Wheeler sent a letter to Karel Kukoš saying how very impressed he was by Karel's research in mathematical physics related to gravity, to general relativity, offering him a visiting position at Princeton University. And Karel is thrilled, and I'm thrilled. I had helped husband this because John Wheeler had a huge appreciation for the kinds of mathematical skills that Karel had. And so Karel was just gearing up to go take up his position at Princeton University when on August 20, the Soviet Union invaded Czechoslovakia. It was a very sad day. My visit in 1967 had seen the difference between the spirit and the feeling of freedom in Prague between 67 and 65. There was a huge opening up by 67. It was the beginning of what became the Prague Spring of 68, which the Soviet Union couldn't take. And so they supposedly, with a number of troops and so forth from other kindred nations in the Soviet bloc, invaded Czechoslovakia, as you well know historically. I then received a letter on August 27 from Karel, written to me and my wife Linda. On August 20, I sent you a copy of my letter to John Wheeler describing my plans to arrive in Princeton after a conference in Tbilisi. By a Czech proverb which says that men intend and God changes, the next night the Soviet troops entered Czechoslovakia. On the 5th day of occupation, Vladina packed in 1 hour the most important things, and we left together with Kamala. We left Czechoslovakia for Austria. Professor Sexel kindly offered me to lend the money for tickets to Princeton and so forth, sorry. And then he goes on and says that they expect to arrive in Princeton at some time in the not-too-distant future. But it just changed everything. Karel then moved permanently to the United States. But Jiří Bičák stayed, and he basically took up the mantle of being the leader of research in this field in Prague, in Czechoslovakia. 1971, the idea of Zeldovich and Novikov paid off. A satellite called the Uhuru satellite was launched. It was designed and built by a team led by Riccardo Giacconi, and they put into orbit around the Earth. And it carried X-ray detectors to look for X-rays from the sky. They saw X-rays coming from this region of the sky. It's a rather large region of the sky, and they couldn't say just where in there the X-rays were coming from, except there was a burst of X-rays that came simultaneous with a burst of radio waves, and the radio telescopes could get very good angular resolution. And so the fact that the burst of X-rays and burst of X-ray and radio waves came at the same moment enabled them to say that this was the location at from which all the X-rays were coming. And that happened to coincide with a star that was seen on this plate. This is a stars field taken by the 200-inch telescope, the Caltech's 200-inch telescope at Palomar Mountain. The star carried a name, HDE 2226868. And this suddenly then became, in some sense, the most famous star in the sky. because this star then was a candidate black hole. This was the Zeldovich-Novikov idea. You had a very heavy, dark object emitting X-rays, and you had the star was going around it, and you had the full spectrum with the optical telescope telling you about the orbital motion. You had the X-rays, you had the radio waves, and it was just a matter of time to collect enough data to be quite sure that this really was a black hole, and just the same thing as Zeldovich and Novikov had proposed. This is an artist's conception. January to June 1971, Jiří Bičák came to Caltech. Now, I by then had built a research group at Caltech. Let me just say a few words about this research group. He came as a postdoc in my research group. He had finished his PhD here at Charles University and had started building his own research group here. He came to Caltech supposedly for a year. My group at the time was immersed in theoretical work on the cosmic microwave background, the Big Bang, quasars, X-ray sources, black holes, pulsars, neutron stars, gravitational waves. I had patterned my research group after that of Robert Oppenheimer. You got some sense of Oppenheimer's research group from the 1930s in the Oppenheimer movie. He had a research group in which he had frequent meetings of the group, and each student or postdoc in the group was expected to report on what they had done since the last meeting. And we would go around, as it did Oppenheimer, from student to postdoc to visitors, talking about what they were doing so that everybody knew what everybody else was doing and everybody got exposed to huge amounts of exciting research that was going on. And basically, it created an atmosphere in which there was just so many exciting ideas now connected to the warp side of our universe, motivated by these observations, but theoretical work related to all this, that it was really an exciting time to be there. And Jiří benefited from this greatly. But unfortunately, he was ordered back to Prague early by the Prague authorities. So he was only allowed to stay for 6 months. But he went back to Prague, and he basically, as far as I am aware, ignited similar warp-side research in Prague and created a research program and a research atmosphere here in Prague. They're rather similar to what I had at Caltech. And I would like to believe that I had an influence on him, and I know what great work he did here and what great impact he had, and how he also was at the same time visiting frequently Cambridge, England, the group of Martin Rees, Stephen Hawking, and so forth, and the Albert Einstein Institute once that was founded in Potsdam. Nearly half a century later, it was my most recent visit here, May 2019. We had a wonderful time with Jiří and his family, many of whom are here in the front row, and it's just wonderful to see you all again. My wife, my second wife, now Carol Lee, came with me, and we do have such very, very fond memories of Jiří, of Prague, and Prague remains my favorite city in all of Europe. Gravitational waves, let me move on. Albert Einstein in 1916 predicted gravitational waves. I like to describe them in terms of what I call Tendex lines that stretch space, say horizontally if the waves are propagating into the screen, and Tendex waves that squeeze the space vertically, so that if this is a set of particles floating out in space, as the gravitational waves go by and space is stretched and squeezed, the distances between the particles are stretched and squeezed. And so you have this kind of a pattern, stretch and squeeze, orthogonal to the direction of propagation of the waves. I use the phrase Tendex for a collection of Tendex lines, and so the gravitational waves are tendencies that stretch and squeeze. Now, gravitational waves are made from the same thing as black holes. They're made from warped space and time. So they're the ideal tool for exploring the warped side of our universe, which, as I say, by the period of 1974, we had lots of observational data about, and it was a very rich period of theoretical work connected to those observational data. Now, there are only two types of waves for exploring the universe, according to our understanding of the laws of physics. Electromagnetic waves, which includes light, radio waves, X-rays, and gamma rays, and gravitational waves. And it was Galileo, 400 years ago approximately, who built a small optical telescope and pointing it at Jupiter, discovered Jupiter's 4 largest moons, and in the process initiated instrument-based, telescope-based electromagnetic astronomy. And there has been an enormous revolution in our understanding of the universe has come out of electromagnetic astronomy, not just optical telescopes, but radio telescopes, X-ray telescopes, gamma ray telescopes, and so forth. So in 1972, I began to develop, together with my student Bill Press and some colleagues and other students, a vision for what we could do with gravitational waves if they could be detected. It's a rather obvious vision, but it was to create gravitational wave astronomy and use this gravitational wave astronomy to explore the warped side of our universe. Ray Weiss, that same year, invented the type of gravitational wave detector that we ultimately used for this purpose, called a gravitational wave interferometer, in which you hang 2 mirrors from overhead supports along one arm of an L-shaped configuration, and 2 mirrors from overhead supports along the other arm. And when a gravitational wave comes by, it squeezes this arm while stretching that arm. Then the next half cycle, it squeezes this arm while stretching that arm. And so you use a technique called laser interferometry that I will go into later on, but not at the moment, to monitor this stretching and squeezing. So that was the basic idea. And that was the beginning of a 43-year effort to use this technique to search for gravitational waves, a 43-year effort that finally had the success that is well known on 14th of September 2015. And that effort involved LIGO, the Laser Interferometer Gravitational Wave Observatory. And so the story then of that 43-year effort is one that I have told many times. I have told it here in Prague at least once, but I think probably more than once. And I also have given a long lecture in Prague here about the detailed history of our coming to understand the warp side of our universe in other ways, including beyond gravitational waves. But what I want to do now is go in a new direction. An aspect of this that I have not talked about before in Prague or anywhere else until very recently, but an aspect that I have come to realize really should have been central to the entire discussion over all these past years. And so I want to bring it out on this occasion in memory of Jiří and his wonderful contributions both to me as a friend and to astrophysics and relativity. So let me begin by explaining what vacuum fluctuations are. If you take a box and you remove from it everything that can possibly be removed, then you still are left with tiny fluctuations of everything that ever could have been inside the box. So you could have had light inside the box, and so you have tiny fluctuations of light particles, photons, fluctuating in and out of existence. And you can't prevent that from happening because the laws of quantum physics demand it. They say that if you knew there were absolutely no photons in there, then the probability would be huge that the photons are going to come into existence immediately in huge numbers. There's this uncertainty principle between existence, between actually existing and coming into existence, basically. And so these vacuum fluctuations are shown here. They have, for the purposes of my lecture, that there are major issues in physics about this, but for the purposes of my lecture, they have no energy and they produce no gravity. And it's true that they have almost no energy, produce almost no gravity. And for the purpose of everything I'm going to do today, that almost we can just ignore. So essentially, that's what the asterisk is. Now, I'm going to show you some paintings by Ludvík Hájek, who's a collaborator of mine. You know that I have worked in Hollywood. Yeah, I've worked on Interstellar. And I had a speaking appearance on The Big Bang Theory. I had one word, a line. I said no. And so that qualified me to get residuals from The Big Bang Theory, which is sort of ridiculous. But anyway, but I have, more recently, I've had a marvelous collaboration with Ludvík Hájek, and we have done a book that is her paintings and my poetry, verse. And we have created this vacuum fluctuations business in verse and paintings. But I'm not going to give you that version. I'm going to give you a prose version, but with some of her paintings. This is just in recent months. So September 1973 in Hotel Rossiya in Moscow, I was there with Stephen Hawking. Jakub Borisovich Zeldovich, shown here on the right, had asked me to bring Stephen to Moscow. Zeldovich wanted to meet him. Stephen was such a brilliant physicist, and he was having such a huge mark on our understanding of general relativity, gravity. And so I brought Stephen with me to Moscow, and we met with Zeldovich and with his student, Alexei Starobinsky, in the Hotel Rossiya in September 1973. And Zeldovich told us a story that was a huge surprise to us. But he had motivated this and said basically that it was obvious intuitively this would happen. And then Starobinsky, his student, said, yes, and I have proved it mathematically using the laws of physics. And the basic idea is this, that black holes spin, and as a black hole spins, it drags space into a whirling motion around itself, like the air in a tornado. And there's a lot of energy in that whirling motion, as was first proved by Roger Penrose back in 1969, and that it's energy that can be extracted. And Zeldovich told me that if energy can be extracted, then vacuum fluctuations will try to do the extraction, always. Vacuum fluctuations have enormously voracious appetites. And so if you have a spinning black hole, vacuum fluctuations coming in from all sides, but here Leah just shows them coming from the left in order to make this easier to understand. They're really coming in from all sides. These vacuum fluctuations come in, they interact with the spinning space, the tornado-like motion, differential rotation of space, basically. The more technical phrase is the dragging of inertial frames, differential dragging of inertial frames. Interact with that and suck energy out of the whirling space and use that energy to turn themselves into real particles. Remember, these vacuum fluctuations are just particles of light or protons or electrons or neutrons fluctuating in and out of existence, the minimum amount of fluctuations that the laws of nature allow. And they turn themselves into a beam of, strong beam of particles coming off the other side. But since the bathing is really from all sides, you get a beam of radiation coming off in all directions. And that will suck up the energy to become outflying radiation, and the black hole will gradually spin down, lose its spin. This was my first realization that what I had thought you could have geometric dynamics, the dynamics of the warping of space and time, without any matter present, and that studying geometric dynamics would be an exciting thing to do. And I indeed spearheaded numerical relativity simulations of geometric dynamics. it would be an exciting thing to do because geometric dynamics must play a big role in our universe. But you can't get rid of the matter. And the vacuum fluctuations, given an opportunity to suck energy out of the geometric dynamics, they will do it. And here was an example. Stephen Hawking, who was a lot smarter than me and thought about things more deeply, went home. This is Leo Halloran's painting of him with his head swirling with ideas. He went home to Cambridge and thought about things for 3 months. And in December 1973, he had an epiphany. He said, if you have not a rotating black hole or even a non-rotating black hole, you have a spherical star, precisely spherical, and it's a very quiescent star, and it is undergoing a gravitational collapse or implosion. As it implodes, a black hole will form at its center. We know this, that it comes from calculations originally done by Robert Oppenheimer and his student Hartland Snyder back in the 1930s. And the black hole will grow as the star shrinks and grow and ultimately swallow the star. And now Hawking said, as it is growing, space around the black hole is expanding. And there's a huge amount of energy in that expanding space as the black hole is growing. And vacuum fluctuations can go in and they can suck energy out of that expanding space in the vicinity of the horizon and turn into particles of real radiation. These particles of real radiation will come off, flowing off the black hole. So you begin with the closest thing there is to nothing, the vacuum fluctuations, and the black hole is being born, and you have particles coming off during the birth. But these particles are held in the sharp gravitational grip of the black hole, and some of them take a very long time to come out. So you have a direct, immediate Hawking radiation, it came to be called. But even 1 million years later, there still is some of this Hawking radiation coming off of this black hole that was born 1 million years ago, that in Hawking's original calculation, that it is created by the vacuum fluctuation sucking energy out of the black hole during its birth. Now, there was huge skepticism about this because it was hard to imagine that 1 million years later you could still have this coming off, but that's what his calculations said. And so he and Jim Hartle did other kinds of calculations by other methods that gave the same answer. And after a few years, it was agreed by the physics community, black holes really do radiate, and they really do radiate because vacuum fluctuations suck energy out of the expanding space in the black hole's birth. Zeldovich, before this, a little bit earlier, had been speculating, and I was only aware of this a bit later when I edited the translation of a book on relativistic astrophysics and cosmology, a book on relativistic cosmology that he and Novikov wrote. And I saw this in there, and I had not really been aware of it. He was speculating about vacuum fluctuations playing in somehow a similar role in the birth of the universe. That in the Big Bang explosion where the universe was born, that vacuum fluctuations may have sucked energy out of the expanding space. But he couldn't make this work. When he tried and his students couldn't make it work quantitatively. He couldn't really make this give anything that corresponded to what we see in the universe today until about 10 years later. His student Alexei Starobinsky and Andrei Linde, also in Moscow, who since has moved to Stanford University, and Alan Guth in Harvard, postulated with strong motivation that in the very early universe, our universe expanded extremely rapidly, exponentially rapidly in technical language. And once they had this, fed this into the issue of the vacuum fluctuations, it became clear that the vacuum fluctuations really could do the following thing, that the Big Bang singularity could have produced only vacuum fluctuations, which fed off the energy of the inflationary space expansion, this very rapid early expansion of space. to produce all of the matter and all of the radiation that we see in our universe today. And here we are with our universe today. We're sitting out in here somewhere long afterwards. But even the seeds of fluctuations from which the galaxies were born appear to have been produced by vacuum fluctuations in the Big Bang, according to calculations by Hawking and others. And so this is really a rather marvelous thing, if true, the idea that the universe could have been born expanding very rapidly, and only the simplest thing it could possibly produce, vacuum fluctuations, were produced there. And those vacuum fluctuations would then suck energy out of expanding space and create everything that we see today. I think that's a great triumph, and I hope it's wrong. And the reason I hope it's wrong is that, and I think it may be wrong, is that I have seen things that I held dear and cherished to myself, and I thought just had to be true, such as the idea that the universe is not expanding, that the universe's expansion is not accelerating today. I've seen them disproved by observation. There have been some huge surprises during my career. And I'm thinking and hoping that there will be a huge surprise here, and that this is actually wrong. But what is right is that gravitational waves from whatever happened in the Big Bang will be amplified by this process of sucking energy out of the expansion of space. And that if we can see those primordial gravitational waves, then they will be a relic of the Big Bang that will carry a mixture of details of the inflation and also of whatever came off the Big Bang. And so this is just a preview of the future. To me, the most exciting thing to come in the next few decades is going to be seeing primordial gravitational waves that came off the Big Bang, and seeing what the spectrum of those waves are, what the statistical properties of those waves are, and using those waves and the observations to unravel the mystery of the laws of physics that controlled the birth of the universe. These are called the laws of quantum gravity, which we don't understand very well at all, and the details of how the universe was born. And so this, to me, as I look into the future, is really, to me, the most exciting thing to come in the warped side of our universe and to come in the next few decades. Let me go on and talk about vacuum fluctuations in other contexts. So in the movie Interstellar, there's a wormhole, and John Wheeler postulated that there may have been a lot of wormholes formed in the very early universe, basically a quantum foam of wormholes. In the movie Interstellar, there is a wormhole that reaches from the vicinity of the black hole Gargantua up to the vicinity of the Earth, and light coming from the vicinity of Gargantua to an IMAX camera produces this image that you see in the movie. And so I was involved in the generating this stuff in the more recent parts of my career. The problem with wormholes, however, as I say, John Wheeler took them very, very seriously, and they are taken quite seriously by a number of physicists today. But there's a fundamental problem, and that is a wormhole left of its own devices. If it's not threaded with anything, if there's nothing inside it, it implodes and pinches off so quickly that nothing can travel through. And so if you want to use a wormhole for interstellar travel and you're a very advanced civilization, or if you want to use it for a movie and you're a scientist trying to preserve his credibility and still using it for a movie, you've got to have a way to hold the wormhole open. And there is a way. That is, you have to place in the throat material that repels gravitationally, and I like to call that exotic matter or exotic material. The only way that we know to make such exotic material is by manipulating vacuum fluctuations. And so now I'm talking about manipulations that a very advanced civilization might do. and the kind of thing that I discuss in my book on the science of interstellar, for example. And let me describe how that conceivably could be. If you take two electrically conducting plates, say highly conducting flat plates, you put them close to each other, you cannot have an electric field parallel to one of these plates, because it will drive a current to flow in the plate, and the current will flow so quickly that it will move electric charges around to annihilate the tangential electric field. That also means you can't have vacuum fluctuations that are parallel to the plate. And so if you have two plates like I'm showing here, and the vacuum fluctuations in there tangential to the plates are highly suppressed. And so you have much less energy between these plates than you would have in the normal vacuum fluctuations. Now, I told you the normal vacuum fluctuations have no energy, they produce no gravity. And so if you bring in two plates like this, and in fact, and this is an experiment that has basically been done, you take handles and hold the plates. Here's one plate I'm holding with this hand, another plate I'm holding with that hand, and you let them move closer and closer together. There's an attractive force that grows very rapidly, 1 over the 7th power of the distance between the plates, it turns out. Where is the energy coming from? The energy is coming from the vacuum fluctuations between the plates, and the energy of the vacuum fluctuations is going negative, more and more negative, as the plates get closer and closer together. And so it has to be that the vacuum fluctuations between those two plates, they're repelling gravitationally. And so that's a very exciting possibility. This is called the Casimir vacuum, and as I say, nobody has seen the repulsion, the gravitational repulsion, but the attractive force has been measured and it agrees with the theory. And so if I take a wormhole like this is a wormhole where I have suppressed one spatial dimension, and so these look like circles, but they're really spheres, two concentric spheres, if you restore the missing dimension. There are two concentric spheres, one inside the other, but they have precisely the same circumference, if you can think about that. So it's sort of like two circles on a cylinder, but they're really spheres on a hypercylinder. The vacuum fluctuations are suppressed between those, and so that is exotic material between there. But the problem, so you've got to hold them apart. You can do that with an electric field line. So you have some electric charge on the plates and electric charge out here, and you have an electric field that has positive energy. But what matters is the energy that you would measure if you're going through this wormhole at nearly the speed of light. And it turns out, when you do a detailed analysis of the sort that Jiří Bičák was really good at, and so in order to hold a wormhole open, it has to be that the average energy that you measure going through this at nearly the speed of light is negative. Well, the problem, of course, is that these plates have to be made out of metal or something, and that's going to contribute some positive energy. And you have exotic material in between, and the question then is whether or not you can have net negative energy, and the answer is we don't know, and it may well be that this is impossible. So let me make a summary. Wormholes in our universe, can they occur naturally? Almost certainly no, except in John Wheeler's quantum foam. Can they be made by an advanced civilization? Possibly. You can imagine an advanced civilization taking a wormhole that's fluctuating in and out of existence and pulling it out of this quantum foam of Wheeler's and enlarging it to classical size. But that's the kind of thing I can speculate about over beer or something, or alcohol stronger than beer. But it's not something that I know enough to be able to give a physics seminar about. But that's the only way I can imagine advanced civilization making a big classical wormhole. Can they be held open? Probably not. It probably requires too large amounts of exotic material. But when speculating beyond the frontiers of firm knowledge, I've been proved wrong many times, and sometimes spectacularly wrong. So don't take too seriously my pronouncement that this is likely impossible. Okay, so I don't rule out wormholes being held open, but my best guess is that they can't be held open. Now, if I do have a wormhole, and I move out that's being held open by vacuum fluctuations that are that in a configuration made by a very advanced civilization. And if I move one mouth out at a very high speed with my wife, Carol Lee, carrying that mouth in her spacecraft, and I'm back here on Earth, and she goes out at nearly the speed of light, then returns. There is something called the twins paradox in relativity that is fairly well known by some people who aren't physicists. And it basically says that she will age much less than I do. So I might wait 50 years for her to come back, and I'm now a really old man. And she may have aged by only 1 year as she was coming back. So looking through space, Carol Lee sees me quite old. But if we hold hands through the wormhole, and she looks at my watch and I look at her watch, they tick at the same rate. So looking through the wormhole, she sees me young. So once she's back here on Earth, and we have the two wormhole mouths, she looks inside the wormhole through her wormhole mouth. She sees a young Kip, but she looks at me and she sees an old Kip looking outside the wormhole. So all I have to do is go over and crawl through the wormhole and come back, and I'll meet my younger self. So I have a time machine. This wormhole has become a time machine during that trip. Now, a postdoc of mine, Sung-Won Kim, and I did a little calculation. Well, for me, it was a big calculation because I hadn't done calculations like this much before. I learned how to do these kinds of calculations. I think in considerable measure from Valery Frolov, who was here at this conference, who mentored me in what's called quantum field theory and curved space-time. But anyway, so Sung-Won Kim and I did a little calculation and found that at the moment it is created, the time machine may self-destruct. In particular, here Carol Lee is holding one mouth, here I am holding the other mouth. The moment that it first becomes possible for something to travel through the wormhole and come back, the moment it started, vacuum fluctuations will do that, moving at the speed of light. So they enter her mouth, they come out my mouth, they go back, and they return at the very same moment as they left, at the very same place as they left, and we have twice as much as we had before. And then they go around again and arrive back at, again, that same point, and we have 4 times as much as we had before, and so forth. So this is, in fact, is an exponential runaway. And it's vacuum fluctuations, it appears, may, in fact, make time machines self-destruct at the moment anyone tries to turn them on. They may be nature's way to prevent you from ever, if you're a very advanced civilization, from ever making a time machine. So this is what this looks like from the outside. Is the explosion actually strong enough to destroy the wormhole? Stephen Hawking made the same discovery together with some students of his at the same time as I did. And then we had a debate back and forth, and he finally concluded that the explosion is only getting strong enough to destroy the time machine at the point where the laws of physics as we know them fail and the new laws of quantum gravity take over. And so until we understand these laws of quantum gravity, which also control the birth of the universe and what goes on inside black holes, until we understand them, we won't know for sure whether time machines self-destruct or not. But Stephen Hawking, who was always willing to speculate, he proposed his chronology protection conjecture that vacuum fluctuations will always destroy a time machine, no matter how advanced civilization tries to create it, destroy the time machine at the moment it's turned on, thereby keeping the universe safe for historians of all species. Let me finally talk about, a question now that is of considerable technological importance. Can we humans manipulate vacuum fluctuations ourselves, for our own technological needs. I've shown you how nature manipulates them to create Hawking radiation, may well have manipulated them to create all the matter and radiation we see in our universe. How nature may manipulate them to make time machines self-destruct. We've seen how an advanced civilization might be able to manipulate them in order to hold a wormhole open. So it's a natural question, can we humans manipulate them for our own technology? And this is a question to whose answer is yes. And this is called quantum precision measurement technology, or QPM technology today. And in fact, this technology has been invented by people associated with LIGO because we needed it for our LIGO gravitational wave observatory. And the issue was that when I was estimating how strong the waves would be that we would see in LIGO, I had a range, and this is estimates that I was making in the mid-1980s. I had a range of about a factor of 100 between the weakest they might be and the strongest they might be. Now, that's 100 in amplitude. That means 100 cubed in terms of the volume of the universe. You would have to search to see the waves. 100 cubed is, well, it's 10 to the 2 times 3, 10 to the 5. It's 100,000. That's an awfully big uncertainty and event rate. But nevertheless, a factor of 100 was enough that we could see the technology we would need to get to the strongest waves in this range that I and my colleagues were estimating, and the weakest waves, and the technology to get to the weakest waves. So that's where we were. But to get to the weakest waves, we had to have this QPM technology. And so it was something I started to push already in the 1980s, that nature might not be kind and we might have to have this technology, and I'll explain this a bit further now. So in order to explain this, let me show you a simple model for LIGO. I've gotten rid of the inner mirrors here, and I just imagine LIGO for simplicity as having two mirrors, a laser, and a photodetector that measures the waves. And I'm going to show you now how LIGO works through interferometry. And so the laser sends out a beam of radiation. Think of that as the waves, and this is the oscillating electric field. The waves go out, they bounce off the end mirrors, they come back to this beam splitter, they interfere in the beam splitter, and if the length of these two arms is identically the same, then they precisely cancel each other going in this direction, and so you don't see any signal. But if the gravitational wave is stretching and squeezing the arms, you see the signal rise and fall out here at this photodetector, and so that is the laser interferometry being used to see the gravitational wave, seeing through the interference between the two arms. Now, the vacuum is not the only thing that's plagued by quantum fluctuations. Everything in the universe experiences them. You and I experience them, for example. And this, in the context of technology, is called quantum noise. The vacuum fluctuations give rise to quantum noise. And there are two dangerous quantum noises in LIGO. The first dangerous quantum noise is a jiggling, a wiggling, a shaking of the mirrors. So I have here paintings of mirrors. They don't look a lot like mirrors, but if you have a really good mirror, it's going to reflect everything that's in the laboratory around you. And so you're going to see all kinds of stuff in that mirror if it's a really good mirror. And so this is an accurate painting by Leah Halloran of these mirrors. But quantum physics says, let me back up. A key aspect of LIGO is that we have spent hundreds of millions of dollars to isolate those mirrors. So the only thing that they do to the laser light is that the center of mass of the mirror, let me start over again. The signal that the mirror's motion puts onto the laser light is coming from the center of mass motion. The mirror's atoms inside it are jiggling thermally, But that thermal jiggling of the atoms inside there is averaged out over time and over the spatial size of the laser beam. Everything gets averaged away, and so the light beam is sensitive only to the center of mass of the mirror. So we think of each of these mirrors as like a 40-kilogram particle. We have two 40-kilogram particles here, and when the gravitational wave comes along, well, let me start over again. You have two 40-kilogram particles, and their positions jiggle like that. Quantum fluctuations, just like an electron inside an atom jiggles. And it's the jiggling of the center of mass of the mirrors. And this is, in technical language, it's due to quantization of the center of mass degree of freedom of the mirrors. And those center of mass degree of freedom will be in some quantum state. And that's what, for the physicists, we're going to be concerned with. And similarly, the light beam, the output light beam here, undergoes a quantum flutter. It jiggles up and down. This is sometimes called shot noise. It's a random arrival of the photons at the photodetector due to quantization of that light beam. I'm sorry, I did have a quantum flutter of the light beam here. But anyway, there it is. Now you saw the flutter, I hope. Okay. It was Vladimir Brzezinski in Moscow in 1968 who told us we were going to have to worry about these quantum noises if we were going to detect gravitational waves, that it was likely we would reach a point where these quantum noises would get in the way of our observations. And that was what I was also finding in my estimates of the weakest, of how weak the strongest waves might be in the 1980s. And so he said, you're going to have to develop something called quantum non-demolition technology, that you have to be able to get a gravitational wave through your detector without the quantum noise of the detector demolishing the gravity wave signal. Carlton Caves in 1981 told us how to do this. He told us how to do quantum non-demolition technology, but it has now become quantum precision measurement technology, or QPM technology. And the key to quantum QPM technology is vacuum fluctuations of light coming in from the direction of the photodetector. Now, the key thing about this is that vacuum fluctuations that come in from the direction of the photodetector, after they go through the beam splitter, whenever they go up in one arm, they go down in the other arm. So they do the same thing as a gravitational wave does. They are anti-symmetric between the two arms. So they produce stuff that is opposite in the two arms, just like a gravitational wave. So these vacuum fluctuations come in, and a key central thing is these mirrors are so isolated that by far their strongest interaction with the external universe is these vacuum fluctuations coming in from the direction of the photodetector, Carl argued. Carl was just finishing his PhD at that time. Nobody else had thought about anything remotely resembled this, and he had this insight that nobody else had had. The vacuum fluctuations come in, they get split, they're fluctuating up and down in opposite directions of the two arms. They bounce off the mirrors, and the superposition of the fluctuations with the steady laser light produces light pressure. And that light pressure is fluctuating, and it is, in LIGO's language, the light pressure from the superposition of the laser light and the vacuum fluctuations, that light pressure is causing the quantum state of the mirrors to be controlled by the quantum state of the incoming vacuum fluctuations, for physicists' language. And for non-physicists, it's just that the fluctuations are controlled. They are controlled by, the jiggling of the mirrors is controlled by the vacuum fluctuations that came in from the dark port. And similarly, the quantum flutter of the light is controlled by the vacuum fluctuations. So vacuum fluctuations control both quantum noises, control both quantum states, in fact. And that was his huge insight. They control the mirror's quantum jiggle, the light's quantum flutter, control those quantum states. And then he had a bigger insight. He said, if we manipulate the vacuum fluctuations in a very special way, called squeezing, which I'm not going to go into, but physicists can go read about squeezed light in many different places now. You squeeze them in very special ways. Then the quantum noise will both types of quantum noise will all be driven into locations where it does not affect LIGO's gravity wave measurements at all. And it was actually Bill Unruh, another young physicist, a former student of John Wheeler's, who did the calculation before Carlton Caves had done it, to show that, in fact, you could get rid of all influence of the vacuum of quantum noise on your gravity wave measurements. And that was just phenomenal. That you could, another way to say it is you can circumvent completely the Heisenberg uncertainty principle for physicists by sending in appropriately squeezed vacuum fluctuations from the dark port. So it was Carl Caves and Bill Unruh who told us what needed to be done. It was Jeff Kimball down the hall from Carl Caves at Caltech who explained how he invented the technology, which is called parametric down conversion in nonlinear crystals for the physicists. Invented the technology for doing the squeezing and the technology for adjusting the so-called squeeze angle. And the LIGO team then worked for 30 years, and this was primarily at the University of Hanover, which is also is a part of the Max Planck Institute in Potsdam, Australian National University, and MIT. These three groups worked for 30 years to perfect this quantum precision measurement technology. That technology is now fully implemented into LIGO, and it's responsible for us seeing several black hole collisions each week, as opposed to one every 6 weeks when we first turned on. We didn't need this, it turned out, in order to see the first waves. The first waves were strong enough that we didn't need this. We do need it now. We are using it now, and it is having a huge impact today. I want to just conclude by saying that this QPM technology, also called quantum sensing, is now being done for atoms, molecules, and nanostructures at Caltech and in private companies around the world. Quantum precision measurement technology is a cousin of quantum computing and quantum cryptography. It grew out of LIGO's needs, but once it was shown by the LIGO team that you could really do this kind of thing, about 10 years ago when things were going sufficiently well, private companies got excited about what they could do with this in nanotechnology and on the atomic and molecular scale. And so this, along with quantum computing, quantum cryptography, makes up quantum information science. These and other 21st century technologies, including AI technology and biotechnologies, have been conceived and developed and matured in university-based laboratories with government funding. And on all of these areas, the conception and the early development and maturation has taken several decades until it would become sufficiently mature that private companies were interested. And so the government funding, particularly in the United States, of this kind of research has really been the seeds for the technology that we count on in the United States to keep us ahead of China, maintain our strength and our technological base of strength. However, Donald Trump is destroying America's capacity for this. He's doing everything he can. He's doing everything he can to destroy our capacity for this because he hates the intelligentsia, he would, I suppose, call them. He hates the universities, and he's going to make the universities bow to his demands if he possibly can. And in the process, he is cutting the budgets for science by more than a factor of 2. And we're no longer, if this really continues, even over a period of the next 2 years, it's going to severely damage our ability to conceive and develop the further technologies of the second half of the 21st century. And so we're counting on Europe to take over. Macron gave a speech a few weeks ago in which he basically said that Europe should be importing the best scientists and engineers that it can from the United States under these circumstances, and I agree. And I'm very sorry that we are leaving you in Europe with this situation. We'll do our best to bring the Trump era to a close in the next 4 years, but in the meantime, we really have to count on Europe to play a bigger and bigger role in this type of thing as when we're no longer able to do so. Thank you.
Thank you very much. And dear professor, if you need position in Europe,
And I, by the way, have a request. Professor Thorne was my father and my mother. I'm Kip. So I do prefer that, and I instituted that in my research group from the very beginning, because I found that if the students held me, I got more fame than I deserved very, very early on. And I found that the students were paying too much attention to what I said and were holding me in too high regard. And so to try to get them down to earth and start thinking for themselves, I, from the outset, started asking them to please call me by my first name. And I ask that of all of you, too. Thank you.
So let us open a discussion. Are there any questions for Kip? So who has the first question? The question disappeared.
Surely you didn't understand everything I said.
Hello.
I can't believe you did.
Thank you for a great talk. My question is, what do you think about future, about Einstein telescope and LISA telescope? How do you think they will
I have great enthusiasm for Einstein telescope, for LISA, for the whole field of gravitational wave astronomy. I hinted at that when I talked about the revolution that electromagnetic astronomy created, as we looked out with very different frequency bands and saw different things. It just hugely changed our understanding of the universe. The one neutron star binary that has been seen, where the electromagnetic waves in all frequency bands known to astronomers, they saw the electromagnetic waves where roughly 25% of all the observational astronomers in the world saw this object with one kind of telescope or another, and the huge set of things that we learned from that. That's a precursor for what we call help me. Multi-messenger. That shows you how tired I am. Multi-messenger astronomy. It's a precursor for multi-messenger astronomy. Astronomy done with the different messengers in different wavelength bands and different kinds of radiation. And I really do think that as the century goes on, as we move into the 22nd century, that there will just be huge changes in our understanding of the universe through the combined observations with gravitational waves, with electromagnetic waves, with neutrino detectors, with particle detectors. And the Einstein telescope and LISA are a major part of that future.
Thank you, and thank you again for the talk. You are a great inspiration.
So if you have a question, please stand up so that we can see you.
Thank you. Thank you for the interesting talk. I have a clarifying question. When you were talking about the wormhole that allows the particle to go through, and then it will cause a runaway effect for another particle, the way I imagined wormholes was that they connect two distant places of space-time, but they are mostly connecting, like if you imagine like a fabric, the particle that enters at one end would still age as it goes through the wormhole, and then age as it returns back. So how come it can be at the same time when it enters the wormhole and then there's the whole journey again?
So it is true, and this is a key part of it, that everything in the universe moves forward in local time. And that forward march of local time shows up in the increase of entropy, the increase of randomness along its path. However, if the universe has an appropriate structure, then it's possible to go out in space and always moving forward in local time, come back to where you started. Now, if you are a fundamental particle, then there's no aging of that particle. The particles are all electrons are identical in terms of their fundamental properties. And so the older version that has gone around and comes back and meets its younger self, well, they really are identical particles, just like all electrons are. And so, but if it's a human being who does this, yeah, you go around and come back, you meet your younger self, but you can tell it's not the same that you have aged. But that's not the case for vacuum fluctuations and for fundamental particles.
Okay, if I can continue in this question. So we already heard today at panel discussion that the time machine would be one of the good inventions from the general relativity. And you described how to create a time machine from the wormhole. Yeah, so let's assume that we have stable time machine. Because there are all these possible paradoxes which one can figure out that something will be logically wrong. And it turns out that for some simple theories, it actually works, right? That actually these paradoxes are not serious. You have some results exactly in this direction. But what do you think about some really interacting systems, strongly interacting systems? Do you think that at the end, these time machines are logically consistent, or that it is no-go?
So the best analyses in this direction that I know are a couple of papers published in 1991, one by Jim Hartle, the other by John Friedman and colleagues, in which they basically are exploring the issue of whether you can do quantum physics in the presence of closed time-like curves, or in the presence of time machines. So they imagine you have a universe where there are no time machines, and then you have a time machine, you have possibility of backward time travel in a finite region of space and for a finite period of time, and then it's impossible again. And they show that using a formulation of quantum field theory due to Feynman, so the so-called path integral formulation, including, I think they've done it with interacting field theories, if my memory is right, but it's a long time since I've looked at those papers. You can evolve just fine. Probabilities are conserved, but information is lost. You have non-unitary evolution in the language of a physicist. And I think those two papers, more or less simultaneous, using different approaches, but both based on the Feynman's formulation of quantum field theory, those two papers make me think it fairly likely that nature can deal with time machines. Whether it does or not is a whole other subject, but that at least using Feynman's approach to quantum mechanics, we as physicists can do sensible posing of initial data and evolving of systems and getting probabilities out. And I think that that's the place I would start if I didn't have other things on my plate. That's the place I would start. And I think this is a very exciting direction for research and pursuing further along the lines of those two papers in 1991.
First of all, really thank you for the lecture. I'd like to ask a bit more philosophical question. Do you think a universal field theory is attainable, or if we ever get there, would it just cause us to discover more things, forcing us to restructure basically our entire understanding of physics?
So let me pose that question. I think you're asking in my own way. We began as physicists with classical physics, no quantum mechanics, and no relativity. And we discovered there were problems, logical problems, and those drove us to introduce relativity, drove Einstein to introduce relativity, special relativity, and general relativity. And so gravity became more complicated there. And physicists were driven to introduce quantum mechanics to deal with observed phenomena. Then it was quite clear that there was logical incompatibility between the quantum mechanics and relativity. And so physicists started to develop quantum theories of gravity. And at each stage, we could see through certain logical incompatibilities that there was a boundary to the domain that our physical laws could operate in, and that there was a region beyond which we needed something new. And so the question is, once we have dug deeper and we really understand the laws of quantum gravity, are there going to be mysteries that we're driven to struggle with that are going to require some layer of reality that goes beyond these laws of quantum gravity? Are the laws of physics nested in such a way that it just goes on and on and on and on forever, or will there be a final theory that really is capable of explaining everything? And I think it's a deep question that's been asked by a number of people, such as Stephen Hawking. And I don't have any answers, and I don't have any opinion. I think it's one of the most interesting questions, but I've chosen in my career to focus on questions where I had some hope of finding the answers. And that's one where I don't have any hope, so I stand back and I'm happy if my colleagues study it.
So maybe one last question, if somebody has.
Hi, thank you for the lecture. This is going to be probably also another question about hopefulness for future. So you talked about the exotic matter. What chances do you give to humanity discovering this matter, or like getting closer to the world where wormholes would be possible? Or is there any research that goes towards that?
I didn't follow
exotic
the question.
matter.
Again?
And what chances do you give with your experience of us being able to achieve that?
Able, you mean to hold a wormhole open? Or?
Yeah.
Yeah.
And other fun stuff.
Yeah. So let me just point you to a book. It's a little bit old. It was 2012. It was by Tom Roman and a colleague, Alan, that's called something like Warped Universes and Time Travel. I've forgotten, but Tom Roman is one of the authors, and I think it's the only book that he's written that's written at a level that is fairly understandable to people who are not professional physicists, and yet it has, as of that date, the best descriptions of what we know about these kinds of problems and what we don't know, and how we came to know what we know and don't know. I worked in this quite vigorously in the 1980s, and LIGO got funded in the 1990s, and I've set everything else aside and have been focused on LIGO, and then quantum precision measurement and geometric dynamics, and have not returned to it. So I don't have a strong view as to what the odds are of really really coming to a reliable answer to whether or not you can hold wormholes open. But if you're interested, the place I would start is this 2012 book by Tom Roman and a colleague. Everett. Yes, Alan Everett and Tom Roman. Thank you.
All right, so before you go home, actually I have one more task for you. So as you've seen, Olda performing the experiment for you at the beginning of the lecture. So he just released this book. It's not an ordinary book. It's actually the book Kip wrote. It's the relativist Bible called Gravitation. And the task for you is to read it before you go to sleep. Okay, so let us thank Kip for amazing lecture.
Thank you very much. I do appreciate it. Thank you.